I would like to dedicate a few minutes to discuss an important concept in approximation theory, linear versus nonlinear approximation. This issue stands behind the scene in the discussion we just had on image priors. As we have just seen, we migrated from L2 to L1 or even L0 in proposing new priors. There are many ways to interpret this modification, such as turning to propose heavy tail distributions, treating outliers better, leading to nonlinear filtering schemes, and shifting from the linear approximation regime to its nonlinear counterpart. I would like to discuss the last in this list, as it is central to our story. Let's start with the linear approximation approach that emerges from the L2. Suppose that our prior is given in this form, which we have already seen. We shall assume that T is square and unitary, such as dCt. The matrix lambda is given here, and as you can see, the first elements on the diagonal are small, epsilon, while the others are big. Let's derive a denoiser relying on this prior. Following ideas we have already met, we aim to maximize the probability of the denoised image while making sure that it is up to epsilon away from y. We modify this optimization as we did before by replacing the constraint by a penalty and by replacing p of x by its minus logarithm. Thus, we get to this equivalent minimization task. The log of the prior is known to us, and this quadratic problem is our new objective. The solution to this problem leads to a linear system of equations and to this closed form solution. Due to the fact that t is unitary, this alternative expression is true just as well. Written explicitly, this is how the denoising process looks. We are to transform y by multiplying by t, then multiply these coefficients entry-wise, and then apply inverse transform. Interestingly, the matrix multiplying the coefficient does not touch the top ones, while almost removing the rest. How do we know which coefficient stays and which goes? The predetermined matrix lambda makes this choice for us. This is known as linear approximation, and the reason is clear. Look at the equation. The optimal x is obtained as a linear operation on y. Now we move to the nonlinear approximation counterpart approach. This starts with the choice of a prior that avoids the L2. Instead, we shall use the L1 or the L0 norms. Observe that we use the same transform as before, but lambda vanished from our expression. Following the same steps as above, the denoising problem translates into this optimization task. While this may look much more complicated from what we got before, this problem too admits a closed form solution. Let's derive it. This is the function to be minimized. By defining z to be equal to t times x, the problem changes into this form. Remember that t is assumed to be unitary, and thus we use the relation x equals t transpose times z. Indeed, for the very same reason, we can modify the expression again and pull t outside of the parenthesis. The last observation we make here is that when t multiplies a vector, it does not change its L2 length, and thus this multiplication can be omitted. Here is our minimization goal, slightly restated, where we have defined the vector z0 to be t times y. This is a vector that is easily computed since both t and y are given. Observe that the penalty function can be written as the sum of n scalar and independent penalties, all sharing the same form, and each governed by one of the unknowns, zk. So we started with one optimization problem where the unknown is n-dimensional, and now we see that it is equivalent to n scalar optimization tasks of this form. How do we minimize these 1D problems? Let's assume that p is 0, implying that we use the L0 norm in the prior. We make this choice only because it is easier to analyze. This is the 1D function to be minimized with respect to z. The unknown could either be 0 or non-zero. If it is 0, the penalty value is 1/2 times z0 squared. If it is non-zero, it better be 0 so as to reduce the penalty as best as we can. In this case, the value of the penalty is lambda since only the second term remains. So obviously, we should choose the smaller penalty value depending on the value of z0. If z0 in absolute value is below some threshold, we choose z to be 0, and otherwise we choose the value z0. This curve describes the relation between Z0 and the optimal Z. This curve is known as hard thresholding. So, solving this optimization task led us to this closed form expression, where the operator S, lambda, applies the thresholding. The process starts by transforming Y, then applying the hard thresholding, and finally applying an inverse transform. By the way, in case you were wondering, if we would have chosen P to be 1, the optimal solution would have been obtained using this red curve, known as soft thresholding. And so, just like in the linear approximation scheme, few transform coefficients are left nearly untouched, while others are attenuated. However, this time the decision which survives the process depends on the coefficient's magnitude, without the need for an external guide. This is the nonlinear approximation scheme. To summarize, we have seen two approximation schemes, the linear and the nonlinear. These are the energy functions they each minimize. Both lead to closed form solutions. The linear simply multiplies Y by a matrix, while the nonlinear does just that, applies a nonlinear operation on the transform coefficients. Both methods temper with the transform coefficients. The linear scheme needs to know in advance which coefficients to leave untouched, typically the top ones, while the nonlinear scheme detects this by their magnitude anywhere in the vector. Do you remember the question we have raised in the context of the JPEG algorithm? We were wondering how come it works so well if it is based on an L2 norm prio? Well, now we have the answer. JPEG starts with a linear scheme. But if a dominant transform coefficient is found elsewhere, it gets a special treatment, and it is not nulled. Thus, JPEG essentially relies on a combination of the two approximation schemes, and it is not a pure L2 based prio.